All right, guys. Hello. This is me doing all the questions that I posted for your practice for this chapter 17. Now, before I get started, I actually have to go over two to three things that I think are very important that I kind of forgot to say. They weren't directly written in the notes, but some of the practice questions at the end of his notes had these concepts. So I'm going to just make sure that you guys know them. So, the first thing is, if you ever have a benzene with a really strong activating group, and the two strongest we're going to consider are OH and NH2. So if you ever have a OH or a NH2 and you decide to do a reaction, let's say Br2 with FeBr3, well, normally you would say, hey, this is the ortho-para director and the next thing needs to go right here. And yes, that does happen. However, because OH is such a strong activator, instead of just going once, this overdoes the reaction and puts the Br on not only the para spot, but both of the ortho spots. So if given a question on the test where they ask you simply this, the answer would be exactly like this. You have to overdo the reaction. Now, what if you don't want it to overdo the reaction? With NH2, it's going to do the same thing. It's going to overdo the reaction. So we need a way to hinder this OH. We need to hinder it so that we can only do the reaction once, and then we need a way to take it off again. So the first reaction we're going to learn is to hinder this, and to hinder your OH, the reagents we're going to use are these. You're going to use NaH with CH3I. So we have done this before. And this pretty much just looks like this. NaH is just a H minus that's going to take this H, thereby forming O minus. When you form O minus, the O minus is going to attack the CH3 and then the I leaves, which is SN2. So my product will be something like this. This is how you hinder the OH. Now, once you do this, again, we have this CH3 right here. Sorry. This is considered hindered now. So after you've hindered it, now if I do the reaction, so let's say I do Br2 FeBr3, it's only going to do the reaction once. It's not going to overdo the reaction. So we're going to put this, and it'll only go once. If this is given to you on the test, this will only happen once. Now, we need a way to take the CH3 off, and this is also something we learned in Orgo 1. You just put this through HI. If you ever put it through HI, you're going to break the ether. So what's happening in here is this grabs the H. So once it grabs the H, it'll form something like this. And then the I is going to be the minus. When I minus attacks here, this comes off like that. So just if you want to know the mechanism. We did this in Orgo 1. So if you do this, you will reform your alcohol. And we stop this reaction from happening over and over again and placing the BRs here and here. So here's what it looks like if you don't hinder. Here's where it would look like if you wanted to hinder. So hinder and like go back, I guess. So that's how you do it for OHs. If you want to ever do this with NH2, then we're going to do it like this. So NH2 is going to do the same old thing. It's going to overdo the reaction. So if you want to hinder it, you have to put it through your acyl chloride. So we have to put it through the same thing we were putting acylation reagents. Except in acylation, we had AlCl3 on the bottom. Here we don't have that. It's just the acyl compound. When you do this, what's happening is this is attacking here and this is going up. But when it comes down, the Cl leaves. This is a reaction we're going to learn actually in like exam 3 almost, so I wouldn't worry about it right now. But what this does make is something like this. Your N, your H connected to this. You form an amide group. Now this is considered the hindered form of your NH2. So now if I put it through a reaction just like before, Br2 FeBr3, it's only going to happen once. You don't have to worry about it over alkylating or overdoing the reaction. So it'll only happen once. But again, just like before, we need a way to go back to the original product, or like go back to this NH2. So to do that, you just need to put it through NaOH with water, which is doing the reverse. You're going to attack this spot, this goes up, when it comes down, this thing leaves. Again, the mechanism part of it is more like exam 3 for you guys, so I wouldn't worry about it, but that's how you take the thing off again. And I would get my NH2 back, and overall I stopped the reaction from happening over and over again. So just keep an eye out if you ever have OH or NH2. They will overdo the reaction, so if you don't want them to, just remember you have to hinder before you go. Okay, that's the first two concepts, or first two reactions I want to let you know. Another important thing that I forgot to tell you guys in class, again, we didn't have that much time, that is regarding synthesis. So there's an official rule, sure Roth probably talked about it if you guys went to lecture, which is if you ever have an electron withdrawing group, or like if you ever have a deactivator on your benzene, then you cannot do any alkylation or acylation. This becomes a problem, acylation. This will become a problem when you try to do synthesis. So let's say you wanted to put a, let's say you wanted to go from a benzene straight to something like this. Let's say you wanted to go something like this. Okay. Both of these things right now are electron withdrawing groups. Both of them are deactivators. Now, what you cannot do is you cannot go first, let's put the NO2, and then do my acylation. So the first step you're doing is HNO3 with H2SO4 to put the NO2 and then acylate. The reason why we can't do that, again, the rule says if you have a deactivator, you're not allowed to do any alkylation or acylation. No carbon adding bonds, carbon adding reactions. So you cannot go NO2 first, then that. So we would actually have to flip it up, and we would have to go this. We would go acylation first, because right now we don't have any deactivators. That would put this. And this is the meta director too, so we can now put the NO2. Again, this chapter, the synthesis is all about what goes first. You might know exactly what to put on, but in what manner you put on matters a lot. What goes first, what goes second. So then you would put the NO2. Again, if you have a deactivator like SO3H, NO2, CN, all the deactivators, do not do any alkylation or acylation. You can only do alkylation or acylation on like a regular benzene or with activators on it only. So keep a lookout for that. And that's it. We're going to follow those rules when we do these questions. So let's start with the questions. The first ones are anti-aromatic, aromatic, and non-aromatic. We did this in class. Now, I can kind of see that all of these are cyclic, so I guess we don't have to worry about that. For the first question, everything over here is sp2, so that's great. Now we just have to look at the Huckel's rule mainly. Over here we can see there's 2, 3, 4. 4 total electrons, that follows 4n. So here, I can write this for you, 4n plus 2. If n was 0, you get 2. If it was 1, you get 6. If it was 2, you would get 10. That's the Huckel's rule. If you have 4n, you can get 0, 4, or 8. So that way we can figure out if something's aromatic or anti-aromatic. So here we're getting 2 and 2, so we're getting a total of 4, which is anti-aromatic. Cool. Next one, this is the lone pair, which normally means sp3. However, let's imagine if we put these electrons in the p orbital. How many total electrons have resonance or on p orbitals then? Well then 2, 2, and 2. So there's a total of 6. Having 6 electrons would mean I am aromatic. So it will be sp2, thereby making this thing aromatic. Next one, this is sp3. There are no electrons to put in the p orbital. It's just 2 H's there. Okay, that's sp3. It's 2 H's. It literally cannot be sp2 ever. This is non-aromatic. Next one, we have 2 electrons that can go in the p orbital. Now some people ask, wait, why can't we put all 4 of them? Well, have you ever seen something like this? Like, would you want to draw a resonance structure where these go here and these go here at the same time? And if they did, you would get something like this in the cyclic product. That's really strange. So you can't do that. You can't have a SPO with 4 bonds with like a 2+ charge. So it's not that. If you have 2 of these, only 2. If you have 2 lone pairs, only one of the lone pairs can go in the p orbital. So here, normally this is sp3, but if I put those electrons in the p orbital, I get 1, 2, 3, 4, 5, 6, which would make this aromatic. So it will be sp2, thereby being aromatic. Same rule here. You put these in the p orbital, you get 6, aromatic. Same thing with sulfur, aromatic. Here, benzene we know is aromatic. Here we see a benzene structure, so even though this is sp3, it doesn't matter. As long as part of your structure is aromatic, you're good to go. So aromatic. This one, just like benzene, we have 1, 2, 3 bonds, and those are the only things we care about. These electrons are just sp2. We don't really care about them being in p orbital. So this is aromatic. This one's also aromatic, 3 bonds. Here, now we have 2, 2, 2, that's 6 again, aromatic. This thing is also sp2. Next one, we have 2, 2, 4, that's anti-aromatic. This one is aromatic, 2. This one is, well, there's the double bond here. That's 2, and here we get to decide. So this one is just like that right there. This is aromatic. This one, double bond, so that's 2, 2. And the last one we get to pick, this one's just like that, aromatic. The last one we have here, this is sp3. Right now I have 2, 2, 2, 6. If I put these in p orbital, I would get 8. 8 would mean anti-aromatic, so it's not going to put them in sp2. It's going to stay as sp3, making it not planar, so it's non-aromatic. I really thought we covered this in class pretty well, so if you're having trouble with this, just practice more, but I really do feel like we covered this in class pretty well. So let's go on to the synthesis. All right, looking at the synthesis, a really good way of doing these questions is looking at the pattern of how everything is connected. Now, how can we get this 1, 1, 2, and like 4 answer? If you remember, if you have a electron donating group on your benzene, the very next thing needs to go para. And then if I'm still listening to this activator, then the very next thing would go here, thereby giving you a 1, 2, 4 answer. So we need to put an electron donating group, add something to this spot, but still have this be the better activator, and then add something to this spot. So let's try to do something like that. Looking at this, we can see this is the 1, 2, 4 spot. So I probably want to add my Br first. Then I can add my NO2 and SO3H. And that's what we're going to do. We're going to start with the benzene. You can add the Br first. The very next thing, Br is a activate, or Br is a deactivator, but it still goes orthopara, so it's going to go over here. The next thing we'll add is NO2. And then, which one's the better activator right now? Well, it's still this Br, so the next thing should go ortho, which is here or here. So we can add the last thing, which is SO3H. Br, NO2, SO3H. So it would be these 3 steps in these exact orders. Now, notice if you tried other stuff, you might get an answer, but let's see. Like if you put the NO2 first, then the very next thing has to go meta to it. Okay. Now you can't put the Br next, because if you put the Br next, it'll be at 1 and 3 position. You want the Br with NO2 to be at 1 and 4 position. So that'll mess it up. So let's say you add the SO3H next. Well, both of these are still meta directors. You're going to listen to SO3, but this is also going to make stuff go here. So then you get caught up in this weird web where you're like not going to be able to put something here for a long time. So let's say like you put a Br here now, well the next thing needs to go here, and then the next thing goes here or here. So it becomes a big mess. You really want to like find that pattern quick, and you're going to get that by just doing a bunch of questions. Okay, next question. Now both of my things are in meta spots. So the way you kind of get the meta spots is, let's put a deactivator, and then the next thing has to go meta, just like we were testing with NO2 and SO3H. Now, looking at this thing, how do you make this thing? We just learned this from the newest reaction. If you want to make that thing, you got to be a NH2 before. So NH2 is normally a activator. So how do you make a NH2? Well, you make a NH2 with NO2. But here we added carbon. So we learned you probably don't want to do this. If you put the NO2 first and then go to put your two carbons, this is not allowed. We said if you have a deactivator, there's no alkylation. So you actually want this thing to be added first somehow, but you also want this thing to be a meta director. So how can we do that? Well, if I just added the ethyl normally with alkylation like this, the next thing would go here. I don't want that. So I'm instead going to do acylation. We're going to start with the benzene, and we're going to do acylation first. If we do acylation, we get this. Notice I'm not writing the middle part. I am really pretty sure you should be able to get this. Like, this is Cl with this, with AlCl3. You can get the middle part, I believe in you. Okay, so we're going to add this. This is the meta director. So the next thing we would want to put in is the NO2. Now we got the NO2. Now we have to reduce the NO2 to the NH2. So here we're kind of doing two steps in once. Look, to reduce a double bond O to the single bond, and to reduce a NO2 to NH2, all you have to do is zinc amalgam with HCl, and it actually gets rid of both of them. So in doing that, I would get this and NH2 at the same step. Now the very last step would be to put this through your acyl compound, the one that they want right here, and this would make your product. This would make the answer go to this. Whoop. Like that. Yep, that's it. If you have other ways you did it, I'll be happy to look at them. The next one is really simple. We should have done this one first, I guess. If you start with the benzene, look at the two things. They're both in meta spot. So between Cl and SO3H, SO3H makes stuff go meta. So I have to put SO3H first, then I can put Cl. Simple as that. You go benzene. If you put Cl first, you get messed up. If you put Cl, next thing has to go here, and then the next thing will go there. I want them to be going meta. So first let's put the SO3H, and the next thing will go meta, which is my Cl, so I'll go right there. That's it, 2 steps. You just need to know the order. The next one, both NH2 and Br are orthopara, but they're sitting in meta spot. But how do you make NH2? Well, you make it from NO2. If I put Br, it's going to make stuff go orthopara, which is not what I want. So just like before, I'm going to first start off with the NO2, like that. Then I can place my Br, which will go meta because this is meta director. So I put the NO2, then I put the Br. And lastly, I would have to reduce the NO2 to NH2. And that's it. That's the answer. Next one. Okay, we have that same position again. 1, 2, and 4. So I probably want to add this thing first, making the next thing go here, making the next thing go here. So let's do that. We're going to start with the benzene. And the first thing we're going to do is add a methyl. After adding a methyl, again, the reagents here are CH3I with AlCl3, or CH3Cl with AlCl3. Then we would want to add the NO2. And then the next thing would go ortho. There you go. Just like that. You add the methyl, you add the NO2, you add the Br. That's it. Next one. Now, how do you make a double bond? This is something new. And also we have a Br and this. Both of them are meta to each other. So one of them, again, has to be meta before the other one can be added. So the way I did this one was, it was a little bit challenging, was first I added this. This will make the Br go meta. So I would get this. Now I just have to make a double bond. Well, first I would want to reduce this double bond O, so I would get this with zinc amalgam. ZnHgHCl would remove the double bond O. Then I did NBS, because that puts a Br at this spot. And then I eliminated the Br with like Naomi home. So NaOMe. That did elimination. That took this H right here, making this go here and this go here. So that would give me the double bond. If you ever want to form a double bond like that, all you have to do is do NBS on a regular ethyl and then eliminate that Br. NBS makes a Br go at the allylic or benzylic spot. This is the benzylic spot, so the Br would go there. So I know that one was a little tough. Here, let's save some space. We'll say this goes straight here, like that. Okay, next one. Again, just like all the other ones, this is the 1, 2, and 4 again. So let's add the 1 first. I would go benzene, add the first one, which is a propyl. Now, notice this is a propyl. If I use alkylation, it's going to make that. It's going to do rearrangement, which I don't want. So I have to actually add it like this, okay? But the next thing needs to go here, and right now this is a meta director, so I have to take the double bond O off. So let's take the double bond O off. Then the next thing will go para, which is my alkylation, or acylation. And then the last thing would be to add the SO3H, which would go at this spot, because this is the best activator still. Cool. Next one. We have the same thing again. I feel like we did this question already. Did we do this question already? No, not really. Okay. Benzene again. You want to add this thing first. So you would do the same thing as the last question. You would add the acylation, take the double bond O off to make your propyl. Then you add your NO2. That would go para. And lastly, you add your Br, which is the final answer. Now, I know I'm doing this super fast, so if you need to like think about it, you can slow down the video or whatever. Okay, now this next one is kind of unique, and I want you to like see this carefully. If you ever get this weird shape, the way this is possible, look at the things. They're both ortho to each other, right? But we have learned that you always want to go para first. So what's happening here was we added this. We put something in the para spot to block this spot. Then we added this and this, only to remove this para thing at the very end. And there's only one reaction we have learned that we can put on and remove completely, and that's the SO3H one. So we can use this SO3H reaction to block the para spot, only to remove it eventually. And that's what we're going to do here. We're going to start off with the benzene and place our methyl. Then we're going to block the para spot. So next thing we do is SO3H. Next, we can add our NO2 and Cl. So let's say we add the NO2 first. And then lastly, we put in our Cl. Now, if you want to go SO3 off, all you have to do is, we did this reaction, it's H2SO4, water, and heat. This removes the SO3H, thereby giving you the answer we wanted. So you can use SO3H as a reaction that blocks the para spot, only to remove it later. So we went this, block this spot, put my stuff on, and take off the block. All right, next one, looking at this question, we can see that having this acylation, remember, we can't add the NO2 first and then do this. That's not allowed. So we're going to probably want to put our acyl compound first. If we put the acyl compound first, then we can add the NO2 next and then this last. We also don't want to do Cl first because that makes stuff go para. So Cl is definitely out of the picture as the first guy or even the second guy, because right when we put the Cl, we're going to start listening to it and stuff's going to go para, which we don't want because everything is meta here. Now again, you don't want to put NO2 first then this because it's not allowed. You can't do acylation or alkylation with a deactivator. So first we want to put this, then put the NO2, then put the Cl. That's the exact order. Any other order would mess up your reaction. You start with the benzene, you put your acyl compound first, then you put NO2, which goes meta, and then you put your Cl. Just like that. Okay. Next question. Here we're getting that same formula again. We want to put this first, then we can put this, then we can put this last. Now notice there's something weird here. Normally you would want to listen to the NH2, so why the heck would we listen to Cl here? Well, the way you can do this is you can put the Cl, then put a NO2, you would still listen to the Cl, so the Br would go here, and then you reduce the NO2. So that's what we're going to do. We're going to start off with the benzene. We're going to first put the Cl. Then we're going to put the NO2. So we're still listening to the Cl for next spot. Then we can put our Br. And then lastly, we reduce the NO2 to the NH2. There you go. All right, last question here. Okay, so they're both in ortho spots. Now, again, when you see this, you want to say, hey, I blocked the para spot only to remove it later. So the way I would do this is you can either think of this thing as the original attacker or this thing. It doesn't really matter. So let's do it like this. We're going to do it as, start with the benzene. We're going to first put our propyl, then we're going to reduce it, then we're going to block the spot, then we can put our NO2, and then we can reduce the NO2 to NH2 and take off the SO3H to make the answer. That one was quite long, but you can also go put NO2, reduce the NO2 to NH2, and then hinder it, then block. I think that's going to take too long. So the way I did it, I think is the fastest. What is it? 1, 2, 3, 4, 5, 6 steps. 6 steps might be too much for your test. For your test, it's probably 4 to 5 steps. But yeah, there it is. I mean, I try to make them kind of hard, I guess. Okay, let's go to the next one. What is this? Okay, so the first thing I want to probably do is take this OH and turn it into this O-methyl. So we learned how to do that. It was NaH with CH3I. So we learned that at the beginning of this video. So once you make that, this is a orthopara and it's hindered. So next thing we can do is add the NO2. Very next thing is we add the NH2, or we reduce the NO2 to NH2. So at this point, who do you listen to? Do you listen to this oxygen or the nitrogen? Well, you got to ask yourself which one is the better activator in this sense. And if you think about it, if this donates electrons, you would form a positive on a nitrogen. If this donates electrons, you form a positive in the oxygen. oxygen is more electronegative and nitrogen's less electronegative. So the better contributing structure is this guy. So nitrogen's considered the better donator in this case, or most cases actually. So we actually are listening to the NH2. Now since we have to add 2 BRs, we don't have to hinder this like NH2. The next two things will go here and here because the pair of spots are already taken. So we don't even have to hinder the NH2. All we have to do is put it through BR2 FeBr3, and it will overdo the reaction and put it in both of the ortho spots. Just like that. So we hindered the OH, we put the NO2, reduced it, and this overdoes the reaction anyway, so you get the last 2 BRs. Alright, next. Here I'm again seeing that pattern. You want to put this, block the spot, add this and this, and then remove the block. So let's follow that pattern. So starting off, I'm going to put the methyl. Then I can block the spot with SO3H. Then, actually, this question is faulted. SO3H is a deactivator, so you're not allowed to add carbons after. I think this, I got this from an old test, and this year they didn't learn that yet. So, I think this question's actually faulted. If you have a SO3H, you're not allowed to add carbons after. So you actually cannot do this. This year they weren't taught that. So this is faulted, but this is not like the real way of doing it. You would want to like add this. Then you would want to add it to the other side. Then you want to reduce both of them with zinc amalgam. And then lastly, remove the SO3H. Now again, this step right here is wrong. You can't do this. You're not, if you have one of these on your benzene already, you're not allowed to add more stuff. So this question's hella faulted. So you can kind of ignore this question, I would say. I just looked at it. Alright, let's look at the next one. So how do you go from a CH3 to making a CBr3? Well, believe it or not, we've done this multiple times. It's just people don't recognize it. If you have this and you wanted to go this, how did we do this part? We did NBS, right? And if we look closely, what did NBS do? There were 3 H's on this carbon. And what NBS did was it removed one of the H's and replaced it with a Br. So if you want C, Br, 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 well, you just got to do NBS 3 times. Or access NBS over HV, which is going to replace all 3 of these with Brs. That's the exact reagents. CBr3 is a deactivator because it pulls too much. It's deactivator by induction. So the next thing must go meta. So my NO2 will go meta. There it is. Next one, we have the hindered nitrogen, and we're putting it through alkylation. Alkylation, the way we learned it, was gonna do rearrangement. So I want you to imagine if the Cl just left, then you get a positive. And then you would do a hydrogen shift. When you do a hydrogen shift, you get the positive in the middle. And then you attack that spot. Now some of you might say, hey, I get a positive. Remember that ring expansion thing? Why don't I do a ring expansion? You can. It's just they weren't testing that here. That was too out of the bloom. So you want to get the positive, and then they wanted to do a hydrogen shift. When you do the hydrogen shift, the positive comes here. So they wanted the benzene to attack this spot. Now the question is this nitrogen electron donating or withdrawing? It's still donating because this goes here and this goes here. So next thing should go para, which is right there. So that's what we're going to do. we're going to have your NH, you have your little benzene, and the next thing would go here. Just like that. You want to attack that spot right there. So you can say, hey, if this is 1, it should attack 2, 3, 4, 5, 6, and 7. So this was 1, this is 2, this is 7, this is 3, 4, 5, and 6. Okay, next one. We know Cn is electron withdrawing or deactivator, and oxygen is the donator. So we're going to listen to this guy. And the next thing should go right here. This is the hindered form of OH, so it's only going to go once. So the answer would be to go in that spot. Let me make this better. You have O, this, Cn. The next thing would go right there. Okay. The next question, we have NO2, which is again withdrawing or a meta director, but this oxygen is a donator. So we're going to listen to the oxygen. And the next thing needs to go ortho to it. So if this was the oxygen, and this is your NO2, the next thing needs to go here, which is SO3H. Just like that. Alright, here we're doing Naomi home, except of ME, we're doing ET. So that normally did elimination, and that's what we're doing here. We have 3 of these, so we should be doing 3 eliminations. So first elimination is going to be get rid of this and form a double bond here. Next elimination is going to be get rid of this and form a double bond here. And the last one is to get rid of this and form a double bond here, thereby making your benzene. So if you haven't seen that before, now you see it. Like that. Now you want to take this and put it through HNO3. Well, between this and this, this donates by inductive effect, this donates by resonance, so resonance wins. We're going to listen to this. The para spot's already taken, so the next thing will go here or here. We need to add a NO2, so we're going to add it to one of the ortho spots, like that. Alright, next one. This benzene is directly connected to a double bond, which is an electron withdrawer or a deactivator. But this benzene is connected to a methyl spot or a methylish spot. So this one's actually donating. So which one's the better activator? Well, this one, because this one is activating and this one is withdrawing. So we're going to listen to this side on the right. And if we're listening to this guy, the next thing needs to go at this spot right here. So we're going to do that. If we listen to this guy, the next thing goes right here and you make your acyl compound. Alright, next question. We have a bromine and we have a nitrogen. The one we listen to is this guy because resonance. So next thing should go right there, which is exactly what happens here too. NH. There's a Br right here. So the next thing goes para, which is Cl. Next question. If I put this through NaH, that takes the H off, thereby giving you O-, which will attack your CH2, making the Br leave. So what we form here is my oxygen with the benzene. This attacks ACH2, which is connected to a pH. Now if you want to make the pH, you can make the benzene here too. There you go. Like that. Alright, we have 2 more questions. This one, okay, so here I think we've done a question like this already, pretty close to it. If you add Br first, next thing would go here, so we're not adding Br first. If you added Br second, let's say we added this, then we added Br, then the next thing would go here. Again, we don't want that. So Br needs to be added third. Okay, between NO2 and SO3H, it doesn't matter which way you add it. You can go SO3 first, then NO2. It doesn't matter. So we'll go NO2. Again, you can do SO3 first, it doesn't matter. Then SO3. and then BR. And that would be the 3 steps. The last question, we'll do it right here, I guess. Alright, so this one was probably the most difficult, from my perspective at least. And the way I did this one was, here, I even have to think about it. Okay, so I called this thing 1 to be used later. I called this 1. Then I took this, here, let's do it right here. I took this and I put it through zinc amalgam. If I put it through zinc amalgam HCl, it will make it go to a methyl because it takes away the double bond O. Then I took the methyl, and that's an activator, so next thing needs to go right there. So I made this add a Br next, like that. Then I took the Br and I made it go to Mg. When I saw this alcohol, I knew this thing was the Mg, so I wanted this little benzene part to be a MgBr, and the other thing to look like this. If I can make that, that'd be good. So that's one combo I could make. The other combo I could have made was this, and I think I used the second combo. That one was if I have an aldehyde and the other side look like this. MgBr. No, I have an extra carbon there, like this, MgBr. If this attacked right here, this would go up to make the alcohol. So I didn't want to do the bottom combo because it just felt like it would be harder to do. This is not a donator, or not an activator, so I would have had to remove this, add the methyl, and then like make a double bond O there again, which could have made the double bond O on this side too, so that would have created problems, which is why I picked the other set. I wanted to do this way. Now, I already have this thing ready to go. The aldehyde part I already have because it was given to me in the beginning. I just have to make this MgBr thing, and that's what I just did on top. If I reduce the double bond O, I go to a methyl. The methyl will add the Br, and then I put this through MgBr. So now I've made this thing. So this thing plus my 1, okay, with the second step being H3O plus, will make my answer. So here, I can write it down for you guys. This would attack the aldehyde, and then you would get this. Just like that, and that's the answer. So that was probably one of the hardest questions. It kind of combines our chapter 15 stuff with the benzene stuff. So if you had trouble with that one, it's okay, I suppose. But yeah, I just put it on the packet because why not? And that's everything. So you have your mock. I hope you're ready for the mock. If you have questions about anything, feel free to email me or whatever. And good luck on the mock and the test. I don't think I'm proctoring the mock. I think there's 2 other instructors. But regardless, yeah, let me know if you have any questions, and good luck. Take care.